So we're looking here at a couple of shell command prompts on a fresh installation of Ubuntu 14.04. Although I want to stress that if you plan to follow along with the demos, and I hope you will, it really doesn't matter what Linux distribution you're running. The features we're interested in here are core technology in all Linux distributions. Now, in terms of the C software development, there's really nothing to install. If I try to install the GCC compiler, we'll find it's already there. And I'm not going to be using an integrated development environment. I'm using the good old-fashioned way of using VI as my text editor, and I'll be doing my compilations from the command line. Now, I know a lot of people don't like VI. Feel free to use Nano or some other text editor, whatever you prefer. So we're going to do a sort of hello world, except that we're going to send the output to a file rather than to the screen. Here's the source code of the program. It looks exactly like the code I showed you in the slides earlier on. But before I build this, I'm going to do one thing here. I'm going to create a bin directory, subdirectory under my home directory, simply with mkdir. And then, at least on Ubuntu, when I log in, that directory will automatically be added to my search path. So if at this point I simply log out and log in again, then if I look at the path environment variable, we should see that indeed my bin subdirectory is now in my search path. There's no absolute requirement to do this. It will just make it a little bit easier to run the programs as I build them. So let's compile our little greet to file program. The -o option on GCC tells it where to put the output, so I'm going to put it in the bin directory, and I'm going to name it after the source file. And then we just want the name of the source file there. And that's done. So now I can simply run the program. And, well, it ran. Let's go over into the other window and have a look and see if we have the file foo that program should have created. And there we see the string hello world. There's no new line on the end of the string, so it's just jammed up against the prompt there, but it does indeed appear to be working. Now, we haven't got any error checking in the code at the moment, so I want to set things up to actually force an error. First of all, I'm just going to write some marker text into the file foo. You'll see what this is about in a moment. And then I'm going to change the permissions on the file so that I no longer have write permission to the file. So if we do an ls-l on the file, you'll see there that I have read permission but no write permission. That means when I open the file in my program, that open call should fail. So let's try running it again over in the left-hand window. Well, there are no error messages. The program appears to have just run to completion. But if we actually look at the file, come over to the right-hand window and look at the file, we'll see that what's in there is simply that marker text that I placed there. The file has not been written to. If we go and look at the code, we can see what's happening. The open call is going to fail because we don't have write permission on the file. It's going to return -1, which is the value that FD gets. The write call will also fail because -1 is not a valid file descriptor, and ditto, the close call is going to fail. But because we're not checking for and responding to any of those error conditions, we're simply not aware as we run the program that anything's gone wrong. So what we need is some error checking. I have a slightly extended version of the program here. And this has error checking in, again, basically like I showed you in the slides. So you'll see we're testing to see if we get a negative value back from open. We're printing out the value of errno if there's an error. We're also calling p-error to get some reasonably meaningful error message. Let's try building this. There's the command line. And now let's try running it. Now you see the output from the printf. It's showing us that we got an error return and that errno is 13. And we see that the p-error call generated the text permission denied, which is what error 13 means. Now there may be situations in the examples as we move through the course where I'll be a little sparing on error checking and error detection in order to keep the code short, but you do need to do this kind of level of error checking and detection on every system call. There are very few system calls in Linux that can't fail at all. Well, that's about as far as I want to take this example right now. We'll get deeper into the actual file I/O stuff in the next module. Let's look at doing the same thing in Python. Now at some point I'm going to install a Python development environment. I'm going to install idle. But to prove a point, I'm going to run our first Python example just using a text editor and the Python interpreter. So let's examine the Python version of the code. This first line tells Linux what interpreter I want to use. Notice I'm using throughout this course Python 3 rather than Python 2. Now in this program we're using an external module called OS, which contains the Python equivalents of the open, write and close system calls that we used in the C code. So we need to import this module. But by and large, the Python code directly parallels the C code that we saw earlier, although notice this rather strange notation in Python 3 for octal constants. So before we run this, let's get rid of the old file foo. And we'll run the program. Okay, well, no errors. Oh, notice there's no compilation step here. Python, remember, is an interpreted language. If we come over here and we have a look at the file that we've generated, then again it looks fine. No new line on the end, just as was the case for the C program, but the file has been generated correctly. Now I'm going to force an error as I did before. So as before, we'll put some marker text into the file and we'll turn off write permission, just as we did before. Now if I come over to the left-hand window and I run the program, what I really want you to notice is the traceback report. This has noticed that the open call has failed, and here you'll see it's printed out essentially the same information that I printed out from the C version of the program, but in this case without any coding effort on my part. Now, in wrapping up this module, I want to acknowledge that a real Python programmer probably wouldn't use the OS module to do this. They'd use the built-in open function that returns a file object and offers a more object-oriented approach. My reason for using the OS module was to demonstrate something that parallels the C code as closely as possible. My point being, I suppose, that although the system calls are usually described in terms of their C language bindings, C isn't the only language that you can make system calls with. We're at the end of this module now. In this module, we've looked at the distinction between kernel space and user space. We've seen what a system call is, we've understood the role of header files, we've seen how to handle errors in system calls, and we've looked at some of the differences between C and Python. In the next module, we're going to focus on the system calls for file input and output, and we'll look at no less than 4 ways to copy a file. I'll see you there.